Hello guys, good afternoon, welcome to my channel. This afternoon I'll be talking about molecular orbital theory with dot and cross approach. The first thing is, what is molecular orbital? Molecular orbital theory is termed when it combines together to give us what we call MO. And what is our MO? Our MO is going to be molecular orbital. And how do we take it to the dot and cross approach? For example, I have beryllium chloride. I also have hydrogen molecule. With this, I can decide to have this in this form. And how do we show the dot and cross parts? The outer electron of beryllium is 2. I will take that to be the cross. While for chlorine, we have 7. I will take chlorine to be the dot. The same thing applies to this. So when you combine it together, you have this. And note, this dot section you have here is what we call the anti-bonding. So when talking about this molecular orbital theory, is that we have this, which is known to be molecular orbital. So we're going to use this here to explain what is bonding and also what is antibonding. And for antibonding, the outer electron will be asterisk. With that, we have what we call sigma asterisk. The sigma asterisk is known to be antibonding. Why for the normal bonding is that we have what we call the 1s sigma. Also, we also have 1s sigma. So it not depend on each one that fall under the 1s bonding only, while the other one fall under 1s antibonding orbital. So let's check for hydrogen gas, or we call it hydrogen molecules. We have this, the cross section. We also have this. So when we combine these two together, it is that they are covalently bonded. So when we go back to the chemical bonding or under covalent bonding, when we talk about when two atoms come together to share the same electron, the first hydrogen while the second hydrogen. So with this, let's show it in molecular orbital structure. I have 1s here, 1s1. I also have 1s1 here. Then the structure goes like this. So the electron here is 1. Why this one is also what? 1. So how do we show which one is bonding and which one is anti-bonding? I have 1s. So this one will move to this place. While this also will also move to this place. So I have 1s sigma 2. That is, I have 2 electrons. While for this asterisk, I have 1s sigma asterisk 0. That is, no electron is here. And again, let's check the electronic configuration of the following diatom. So I have nitrogen gas, I have oxygen molecule, and also I have hydrogen molecule, as explained earlier. So I won't be going with this, but when we get to bond order, I will start with these 3 compounds. So let's start with hydrogen. According to the first 20 elements, the outer electron for hydrogen is 1. So I have, if it is hydrogen molecule, we have 1s sigma 2, 1s sigma asterisk, we have a 0 here. So for helium we have 2. So for us to be able to do this, let's take it back to the molecular orbital structure where we have this. So I have 1s here, I also have 1s here. Don't forget the electronic configuration of helium is 1s2. So if you are having helium to be a diatoms, so I have 2 here, I also have another 2 here. That is, helium appear twice, so these 2 here will come here, while this one here will move to this, the antibonding. So if you want to show the bond order, I have 1s sigma 2, which is this, then 1s sigma asterisk 2, which is this, and don't forget this asterisk here stand for antibonding. The next one, after helium we have lithium. Lithium is 3. So the next thing to do is write out the electronic configuration of lithium, which is 1s2, 2s1. And if we should take lithium to be a diatoms, which is 2 of lithium, don't forget your molecular orbital structure. So I have this 1s, 1s, and note the 1s here is 2. So 1, 2, and mind you, we have 2 lithium, that is, they are diatoms. So 1, 2. This will come here. This also will what? Come here. And don't forget, you have to what? Asterisk this place to show that you have an antibonding orbital. And the last one for lithium, 1s2, 2s1. So this one is 2s. You have to draw another molecular orbital, which is this. What did I have here? 2s, 2s. 1 electron here, 1 electron here. So one of these will move here, the other one will also what? Move here. This particular place must be filled up before the antibonding orbital. So if we want to write the bond order now, the first one here is 1s sigma, we have 2 here. Sigma, sigma. So I have sigma here, we also have sigma here. Then the second one, which is this place, we have 1s sigma asterisk 2. While the other one is 2s sigma 2, 2s sigma asterisk, we don't have anything here, which is what? 0. So with this now, we can proceed to what we call bond order. We call it bond order. And what is bond order? Bond order is a value obtained between the difference of bonding order and non-bonding order, which is half. The formula is bond order is equal to half. In the brackets we have bonding order minus anti-bonding order. So with this formula, we can go back to the example which I dropped earlier, as we have nitrogen gas, oxygen gas, carbon dioxide. We also have oxygen molecule with a negative power, which is the valency. So let's pick this one by one with respect to molecular orbital theory and also using bond order formula. The first one is nitrogen gas. So the first thing we are going to do is we have to split this nitrogen into 2 and then take the electronic configuration. The first nitrogen is here, the second one is here. So I have 1s2, 2s2, 2p3, because the atomic number of nitrogen is 7. 1s2, 2s2, 2p3. So let's take the bonding orbital structure. I have this for 1s. So let's pick it one by one. The 1s here, how many does it have? We have 2. 1, 2. The second one, we have 1, 2. So don't forget, here is our anti-bonding. And the purpose of using this bond order is for us to check the stability of elements. So we have 1 and this also. That is, these two will come to this place under the sigma bonding. Here we have sigma bonding for anti-bonding orbital. So the next one is 2s2 for the 2 nitrogen. I have this, I also have this. Mind you, for 2s2 we have 2. So 1, 2, 1, 2, and here is our bonding, anti-bonding orbital. So the last one is 2p3, which we are going to have both the sigma bond and the pi bond. We have this structure. So our 2p3, 1, 2, 3, 1, 2, 3, and here we have it to be sigma. Here we have pi asterisk. Here we have sigma asterisk out there. So what do we have here? 2, 1, 2. Also here we have 1, 2. Then let's pick the remaining one of the 2 nitrogen. This will come here, while the second one will come here. So with the formula given for bonding orbital, I will make it short. So we have bond order, they are half of bonding orbital minus anti-bonding orbital. So let's check out which one is bonding orbital and which one is anti-bonding orbital. So for nitrogen molecule, the first one we have there is 1s sigma. The elements there is 2. The second one, 1s sigma asterisk. We have 2 electrons. Then let's move to 2s. 2s sigma asterisk 2. Sorry, we have 2s sigma 2. Then the second one is 2s sigma asterisk 2. So let's move to the p orbital, where we have 3 each for the 2. So the first one outside here, we call it 2p sigma 2. Then the inner one is pi. So we have 2p pi 4. Because when we count this, we have 2, 4. Then the 2p pi asterisk, we have 0. So let's check which one is bonding orbital and which one is anti-bonding orbital. Don't forget, the one with asterisk is the anti-bonding orbital. So let's check. For bonding orbital, we have 2, 4, 6 plus this, making it 10. So we have 10 minus the anti-bonding. We have 2, 4. So we have 4 here. So 1 over 2, 10 minus 4 will give us 6. Half of this we have 3. So it is stable. Then another example of this bond order. So for the oxygen gas, oxygen molecule with negative sign, we take the electronic configuration, and don't forget the atomic number of oxygen is 8. So for this negative sign, it means that oxygen accepts 1 electron. So we have 1s2, 2s2, 2p4 for the first oxygen, this. While the second one, for the 1s2, 2s2, 2p5, don't forget the negative sign you have here makes the p orbital to have 5 electrons. So let's pick it one after the other. For 1s, we have this. And here is our antibonding orbital. So for our 1s here, I have 2. 1, 2, 1, 2. So one of these will come here, 1, 2, 1, 2. Then the second one, which is 2s. And here we have 2p, 2p. So for this, are you saying it now? So for the 2s, we have 1, 2, 1, 2. Don't forget, here is our antibonding orbital. Why for 2p? So for 2p, we have 2p4. 1, 2, 3, 4. Then the second one, which has a negative power, we have 1, 2, 3, 4, 5. So don't forget your inner pi. So for this we have 1, 2. Then the second one move here, 1, 2. Then this will move here, this will move here. So let's pick 2 from this place. 1, 2. The second one, 1, 2, and the last we have what? 1. And here is pi steric. So let's show the bond order. The first one for 1s, we have 1s sigma 2, 1s sigma asterisk 2, and the second one 2s sigma 2, 2s sigma asterisk 2. Then here, don't forget, is your sigma. So we have 2p sigma 2. Then the inner one, which is for the pi, we have 2p pi 4. If you count it, 2, 4. Then the last one is 2p pi asterisk 1, 2, 3. We have 3. So let's check which one is bonding order minus the antibonding order. For the bonding order, we have 2, 4, 6, 10. So 1 over 2 divided by 10 minus the antibonding order, 2, 4. Then we have 3, making 7. So we have 1 over 2, 10 minus 7, we have 3. So for this, we have 1.5, which is stable. Note one thing, if it is less than 0.5, it is not stable. So let's take the last one, which is carbon 2 oxide. Of carbon 2 oxide, the atomic number of carbon is 6, oxygen 8. So let's get out the electronic configuration. 2p2, then we have 1s2, 2s2, and 2p4. So let's draw the bonding order structure. So we have this. 1s from carbon, 1s from oxygen, and both carry 2. So we have 1, 2 for carbon, 1, 2 for oxygen. So we have 1, 2 here, 1, 2 here, and here is our antibonding. Then the second one is 2s. 1, 2, 1, 2. So we have this here, and this is our antibonding. Then the last one is 2p. So 2p for carbon we have 1, 2. 2p for oxygen we have 1, 2, 3, 4. So the inner pi asterisk, then we have pi here, here we have sigma. So for this, we move it here, then these two will come here to the pi, while here will come to what? Come to this pi. So let's get out the bonding orbital. So I have 1s from carbon, sigma, we have 2. The second one, 1s sigma asterisk 2. For 2s, 2s sigma 2, 2s sigma asterisk, I also have 2 there. Then the second one is 2p sigma 2. Then for the pi inside the orbital, molecular orbital structure, I have 2p pi 4. With this, we can now take it to the formula we have here, that bonding order is equal to half of bonding orbital minus antibonding orbital electron. So we have this. Our bonding orbital electron can put E here, we can also what? Put E here. So for the bonding orbital, the one that did not have a steric, 2, 4, 6, we have 10. Minus antibonding orbital electron, 2, 4, 4. So we have 1 over 2, 6, half of 6 we have 3. So it is stable. Note, for every molecular orbital theory, their energy level must undergo 4 pairs of electrons. Thank you for watching, and don't forget to subscribe.